Hello my friends and welcome back to the You Can Do TV channel. At the Cool Spring Electric Museum in October 2020, several historic gas engines were demonstrated in operation, including the massive 1925 Otto engine. This single-cylinder engine, one of only 5 ever built, was demonstrated running with 2 large flywheels spinning. The engine uses compressed air to initiate the first sparks. Once combustion begins, the cycle is self-sustaining. Fuel is injected and mixed with air, ignited by a combination of a magneto and a spark plug. The Otto engine operates at a regulated speed of 180 revolutions per minute, producing 175 horsepower. The engine uses a throttle governor to regulate speed by adjusting the air-fuel mixture. The piston, with a 21-inch bore and 30-inch stroke, moves inside the cylinder to convert combustion energy into mechanical work. The massive 9-foot 1-inch flywheel stabilizes the rotation and maintains momentum between sparks. Throughout, the camera captures the coordinated motion of the connecting rod, crankshaft, and flywheel. The exhaust valve opens sharply with each acceleration stroke, releasing the combustion gases. The vibrations and sounds of the 49,000-pound engine are evident as it smoothly accelerates through each cycle. The operator monitors the engine and makes small adjustments to ensure continuous operation. The video also shows other engines starting and running, each controlled manually or by a governor. The display showcases the robust engineering of the original gas-powered engine and highlights the mechanical precision involved in keeping these historic machines in working condition. The startup process of the 600 HP Snow engine begins with manually rotating the massive 10-ton flywheel using a long metal bar inserted into one of the flywheel sockets. Multiple operators take turns applying force, slowly bringing the flywheel around to build up enough momentum for the engine to start. This manual cranking also ensures oil circulates and the pistons move freely within their cylinders. Once sufficient revolutions are achieved, operators prepare the make and break ignition system, which uses 4 igniters per cylinder. Each pair of igniters is powered by a separate coil on the ignition panel, allowing redundancy in case of igniter failure. With the ignition system engaged and gas valves partially opened, natural gas is introduced into the combustion chambers. As the flywheel continues spinning, a spark ignites the gas-air mixture and the engine roars to life. Combustion begins within the 6 combustion chambers, 2 per cylinder. The pistons drive the connecting rods, crankshaft, and flywheel, maintaining rotational motion. During the running phase, the engine's operation is closely monitored. Operators adjust the fuel valve handles manually to ensure each cylinder receives the correct amount of gas. These settings affect the timing and smoothness of the engine's strokes. Additional mechanical adjustments are made while running, including tightening bolts, checking lubrication, and adjusting tappets and linkages. The huge components move in synchronized rhythm, producing a deep, thunderous pulse that echoes through the building. The shutdown procedure starts by slowly closing the gas valves to cut off the fuel supply. As less gas enters the chambers, combustion slows. The engine's tempo decreases, and the sound changes noticeably. Once all cylinders cease firing, the flywheel continues to spin under its own inertia before gradually coming to a full stop. The ignition system is then switched off, and a final inspection is performed to ensure all systems are safe and inactive. The massive engine sits still, completing its powerful yet graceful demonstration. The Cooper coreless steam engine begins operation as steam flows into the cylinder, actuated by the distinctive coreless valve gear system. The engine's massive piston reciprocates horizontally, transferring force through the connecting rod to the 25-ton crankshaft. As the crankshaft turns, the 25-foot 4-inch flywheel slowly gains momentum. The flywheel, composed of 12 bolted segments, rotates steadily, demonstrating the stored torque of this 60-ton component. The valve gear visible in motion controls steam admission and exhaust with high precision. Its rotary valves open and close rapidly, allowing for efficient steam expansion and contributing to the engine's regulated speed. A centrifugal governor atop the engine automatically adjusts the valve timing to maintain consistent revolutions. As the engine runs, the rhythmic movement of the valve linkage, flywheel rotation, and the measured beat of the exhaust cycle reveal the engineering elegance of coreless design. The entire assembly operates smoothly, delivering power through the line shaft system while showcasing the impressive mechanical synchronization achieved over a century ago. At Mill Meese, steam is generated in the boiler house. Coal is fed into an external hopper by a tractor, then lifted by an Archimedes screw into two smaller internal hoppers. Timed feed mechanisms maintain a steady coal supply to the furnaces, where adjustable force draft levers control the fire's intensity. Hot flue gases circulate through and beneath the boiler, ensuring efficient heat transfer. Steam from the boilers passes through the wall into the engine hall and enters the steam chest. It is then directed by valves into a horizontal compound rotary tandem engine. This engine consists of high and low pressure cylinders aligned in tandem. The expanding steam drives the pistons, which rotate a flywheel to maintain momentum and drive high pressure pumps. These pumps deliver water 5 miles away to Hand Church Reservoir, 350 feet higher in elevation. To start the engine, a small steam-powered barring engine is engaged with the flywheel to rotate it past top dead center. Once running, the main engine operates smoothly and quietly, earning it the nickname the Gentle Giant. At Mill Meese Pumping Station, the water pumping process begins with the operation of steam-powered machinery. Steam is raised in 3 Lancashire boilers, with their efficiency enhanced by a greens economizer that recovers heat from exhaust gases. Once sufficient steam pressure is achieved, it is delivered to 2 large horizontal tandem compound engines fitted with coreless valves. These engines drive the lift pumps that draw water from 4 deep boreholes located on site. Each lift pump is connected to the crankshaft of one of the steam engines via a robust beam mechanism. As the engines run, they produce a smooth reciprocating motion that powers the vertical lift pumps. These pumps raise groundwater into an intermediate underground storage tank. Once the water reaches this tank, it is pumped again using ram pumps, which are also mechanically driven by the same steam engines. The ram pumps apply additional pressure to push the water onward, likely towards a reservoir or distribution system. Throughout operation, engineers monitor pressure gauges, adjust steam valves, and lubricate moving parts to ensure smooth functioning. The rhythmic motion of the pistons, flywheels, and beams reflects the precision of early 20th century steam engineering. The coordination between the steam generation system, the coreless engines, and the dual-stage pumping mechanism demonstrates the integrated design of the station, allowing continuous and efficient water supply from the boreholes to the wider network. To start the big red coreless steam engine, operators first ensure it is in the correct starting position. If necessary, a small barring engine is used to rotate the main engine into alignment. In this case, the left crank was already correctly positioned, so the barring engine was not needed. Next, lubrication is activated to ensure all moving parts are protected. The main steam valve behind the engine is then turned on. A wrench is used to manually open the inlet valve of the high-pressure cylinder. Steam enters, and condensed water is expelled from the cylinder. The inlet valve is then closed temporarily before reopening it while adjusting the main steam valve for a smoother start. As the engine begins turning, components such as the flywheel, pistons, rotary inlet and exhaust valves, governor, dashpots, and linkage bars engage. The governor, driven by the crankshaft, senses the speed. As the speed increases, its flyballs rise, twisting the control shaft. This action adjusts the timing of the inlet valves by segment gears, shifting from a late cutoff, more power, to an early cutoff, less power, depending on load conditions. The low-pressure cylinder receives expanded steam and features a valve gear primarily for balance. Its valve timing can be adjusted manually using a hand wheel. The rear oil pump and condenser's air pump are also driven by the engine. To shut down, the steam valve is closed, followed by the condenser's valve. Finally, the engine is stopped precisely at its correct rest position. The simulated operation of the Titanic's 1912 steam engine begins as steam generated from 29 boilers, 24 double-ended and 5 single-ended, fueled by 159 furnaces, is directed into the 2 massive reciprocating engines. Each engine, measuring 63 feet long and weighing 720 tons, receives high-pressure steam into its high-pressure cylinder. The steam then expands and moves to the intermediate and low-pressure cylinders sequentially, driving the triple expansion process. Pistons inside the cylinders move back and forth, turning the large crankshaft below. This rotary motion is transmitted to the propeller shaft, providing thrust to move the ship. Exhaust steam is collected and reused or released into the condenser, completing the cycle. The operating cycle begins by positioning the engine at one of its two starting points, identified by 180-degree marks on the beam floor. A small barring engine is used to rotate the massive flywheel, which spans 8.23 meters, into position. The main steam valve is then opened, sending steam into the high-pressure cylinder located beneath the intermediate pressure cylinder. Steam first expands in the high-pressure cylinder, then passes into the IP cylinder, and finally enters the large-diameter low-pressure cylinder in the basement. This triple expansion process maximizes efficiency by using the steam 3 times. Each cylinder drives a rocking beam 13.1 meters long. The low-pressure cylinder connects to a grasshopper counterbeam, providing nearly parallel motion to its piston rod. To ensure accurate linear motion for the air and water pumps, additional crossheads are attached. The beam's motion also drives a sewage pump via a large plunger. Exhaust steam is drawn through a condenser by an air pump, while another pump circulates cooling water. The coreless valve gear with steam cutoff and exhaust valves regulates steam flow, completing the power cycle. The Cooper-Bessemer Model 10 starts with a steady rotation of its massive 7-foot flywheel. As the two-cycle engine fires, the power piston drives the crankshaft, which simultaneously operates the compressor piston on the opposite end. With each cycle, air is drawn in, compressed, and discharged through valves. The smooth, rhythmic motion delivers a consistent supply of compressed air to simulate its original function, powering oil well pumps. Steam enters the Paxton low-pressure steam turbine at 200 kilopascals, causing the rotor to spin. As the steam expands through the turbine blades, it transfers thermal energy into mechanical rotation. The shaft connected to the rotor drives a generator or mechanical equipment, producing useful power. The turbine maintains steady operation under full load, using energy from various heat sources. Exhaust steam exits through the outlet after energy extraction. The system demonstrates stable rotation, efficient power output, and compatibility with diverse steam circuits powered by solar, fossil fuels, or geothermal energy. Steam enters the cylinder from the water tube boiler, pushing the piston back and forth. This linear motion is converted into rotational motion by the connecting rod and crank. The flywheel maintains momentum and stabilizes rotation. The governor regulates engine speed. Exhaust steam exits the cylinder after pushing the piston. The steam turbine APU also runs simultaneously using steam from the same boiler system. Two 70-horsepower steam engines are coupled in line with crankshafts staggered at 90 degrees to form a single 140-horsepower engine. This setup delivers 4 power strokes per revolution, ensuring smooth and continuous power. 4 150 kilograms flywheels maintain constant speed. The engine drives heavy machines like sugarcane crushers or stone crushers and can power an 80 kilowatts alternator. It operates with a 2-ton boiler and is ideal for rural industrial applications. Frequency variations are minimal in captive use, but it's not suited for grid feeding. The steam engine shown is a single-cylinder, double-acting 25 HP unit connected to a 15 kVA alternator via pulleys and 3 V-belts. Steam is generated by a boiler and passes through a water separator to remove condensate, ensuring dry steam enters the engine. A Buckeye-type governor regulates the engine speed. The water separator uses tangential entry and central outlet to efficiently separate water, while an oil separator collects and reuses lubricating oil. Before starting, 3 valves must remain open and be closed after the engine runs. An arrow mark on the engine and flywheel must align to ensure correct rotation direction during reversal. Then, the eccentric must be loosened, adjusted, and retightened. The steam engine is run at half pressure for testing due to the boiler's limited capacity. During operation, steam exhaust is visible, and the system runs at 1658 RPM. Electrical output parameters such as frequency and amperage are monitored, ensuring stable performance. The setup lacks a foundation, as it is temporarily installed for testing before shipment. Jamie and Luke Coates begin the startup of the Rustin Hornsby Model LE paraffin engine by first ensuring that the fuel supply is ready and the fuel lines are clear. They then open the air valve to reduce initial compression, allowing easier turning of the engine. Using a blowtorch, they heat the engine's hot bulb until it reaches a high temperature, sufficient to ignite the incoming fuel-air mixture. Once the hot bulb is adequately heated, they begin cranking the engine manually with the starting handle. Several strong rotations are required to build up compression. As the piston compresses the fuel-air mixture inside the cylinder, the heat from the hot bulb causes spontaneous ignition, leading to combustion and initial movement of the engine's flywheels. After ignition, the engine begins running intermittently before stabilizing. Jamie and Luke monitor the operation, adjusting the air and fuel mixture to help the engine reach a smooth and steady idle speed. During this process, the engine transitions from using starting fuel to paraffin, its main operating fuel. Once the adjustments are complete and the engine stabilizes, it runs continuously and efficiently. To start the 50-horsepower White and Middleton engine, the flywheels are first rotated manually to build momentum. As they turn, the make and break igniter, powered by a battery and induction coil, creates the initial spark for combustion. Natural gas enters the combustion chamber, controlled by a centrifugal flyball governor. The engine fires when power is needed and idles when not, using the hit and miss method. The 2 concentric pushrods operate both the exhaust and fuel valves in sequence. As the engine runs, the piston exposes an auxiliary exhaust port at bottom dead center, aiding in cooling. Once combustion stabilizes, the engine maintains steady operation. At the 2012 Summer Show at the Cool Spring Electric Museum, several large internal combustion engines were put to use. The first engine in the video, located at the Nate Lillibridge station, is a rare 300 HPH-shaped 4-cylinder gasoline engine built in 1913 by the Miller Improved Gas Engine Company. During operation, its distinct firing sequence and smooth mechanical motion spins the large flywheels. Although the Ingersoll Rand Imperial compressor it once drove is still being rebuilt, the engine itself runs very smoothly. Next up is a 65 HP Blaisdell Machine Company engine compressor assembly located at the Windy City Rental Building. Built in 1916, the engine's mechanical linkage can be seen driving an integrated compressor. The air produced will be used to operate an oil well pump. The steady hum and rotation of the flywheel highlight its reliable compression cycle. The Windy City building and machinery have been completely relocated to the museum. The final engine on display is a 1925 Otto 175 HP engine, installed in the Electrical Technology Building. With its large single-cylinder and twin flywheels, this engine powers the Worthington water pump. When running, viewers can see its slow but powerful strokes as it pumps water, demonstrating the enormous torque generated for its size. All three engines ran impressively during the event, demonstrating the mechanical heritage held at the museum. The starting process of the Foos 15 HP throttle-controlled engine begins with the flywheel being manually rotated to position the piston just past top dead center. A torch is used to heat the hot tube igniter, ensuring reliable ignition at startup. Once hot enough, fuel is introduced and compression begins to increase. The operator then rotates the flywheel sharply, causing the engine to fire and gradually take over its own power. As the engine gains momentum, it begins to run smoothly and steadily, controlled by a governor-controlled throttle system. A kW high-voltage generator provides a steady spark, while a large electric-lit flywheel maintains a steady rotational speed. The engine's motion is transmitted via a belt drive to a nearby General Electric DC generator. When the engine reaches operating speed, the generator begins to generate electricity. The second starting process is performed in the same way, with the mechanic manually rotating the flywheel again and introducing fuel. This setup powered the incandescent lamps at Lillibridge Station. The engine runs with a deep, steady roar, a sign of steady combustion and smooth mechanical operation. This carefully restored system not only demonstrates the elegant design of the Foos engine, but also faithfully recreates the way it once powered oil fields and electric lights. The starting process begins by manually rotating the flywheel to ensure the engine is free and properly aligned. Next, compressed air is introduced into the cylinders through valves to start the rotation. As the large flywheel begins to rotate, the operator monitors the engine's rhythm and adjusts the airflow accordingly. As the engine gains enough momentum, fuel is gradually injected into the cylinders. Ignition occurs from the residual heat in the combustion chamber, allowing the engine to start firing under its own power. During the transition from gas to fuel starting, careful attention is paid to the exhaust and ignition sequence to confirm consistent operation. The operator then adjusts the fuel rack and control system to stabilize the engine speed. Once the diesel engine is running smoothly, the compressed air system is disconnected and the engine continues to operate on diesel fuel alone. Final checks include checking oil pressure, fuel supply, and engine temperature to ensure consistent performance. The engine is now fully operational and ready for demonstration. The startup of the Fairbanks Morse Model 32 begins by rotating the flywheel using compressed air to bring the engine up to starting speed. As the flywheel spins, fuel is gradually introduced into the cylinders. The engine begins firing with heavy puffs of exhaust and rhythmic knocks. The operator adjusts the fuel settings and watches for smooth and consistent combustion in all three cylinders. As the engine stabilizes, the exhaust clears up and the engine runs steadily at low RPM. Vibrations decrease and the operator monitors gauges to ensure proper oil pressure and function. Once fully running, the engine's mechanical linkages and moving parts operate smoothly. The starting process begins with the flywheel being manually rotated to check for free movement. The pilot cup is filled with fuel and closed by the operator. Next, the release lever is activated and the flywheel is rotated rapidly by hand to generate momentum. After a few revolutions, the release lever is released, allowing the engine to fire. The engine fires and begins to run steadily. After running, the governor and lubrication systems are checked to ensure proper operation. The flywheel continues to rotate, smoothly powering the engine side shaft and related mechanisms as it reaches maximum operating speed. To start the Buckeye Model L, a kerosene torch is used to heat the ignition bowl for up to 20 minutes. This preheats the chamber to vaporize the fuel. The engine is then barred over to set the piston slightly past top dead center. Next, the fuel pump is primed and bled to ensure fuel flow. Once ready, compressed air is used to spin the engine and initiate combustion in the preheated chamber. When running, the ignition bowl maintains heat to sustain operation without further torch heating. The starter pushes the starter lever. Compressed air is applied to initiate rotation. As the engine turns, fuel injection begins automatically. Combustion follows, and the engine gradually takes over under its own power. The large connecting rod becomes visibly active through the crankcase window as the engine runs steadily, producing its characteristic deep exhaust rhythm. The operator slowly opens the main steam valve to allow steam into the cylinders. As pressure builds, the twin V cylinders begin moving, gradually increasing in speed. The large flywheel turns steadily, transmitting power to the alternator via belt drive. Once stable operation is achieved, the engine continues running smoothly at full speed. The startup of the 1923 Fairbanks Morse YV oil engine begins by opening the compression release valves and barring the engine over manually until the front cylinder is about 10 degrees past top dead center. Kerosene burners are then lit to heat the combustion chambers. This process takes 5 to 10 minutes, as the starting tubes must be hot enough to ignite fuel in the engine's low-compression semi-diesel chambers. Once heated, the compression releases are closed. The lubrication system is primed, followed by the fuel system, using the starting levers to pump fuel. The starting levers are left in the run position while the compressed air valve is opened. The engine starts and runs steadily at 257 revolutions per minute, producing 100 horsepower and 2,044 pound-feet of torque. To shut it down, the operator pushes both starting levers inboard, cutting off fuel flow. Water tube boiler testing begins by burning a small fire under the steam tube to create pressure. As the fire continues, the pressure gradually increases, reaching 30 psi. Additional rods are added to the fire to maintain the combustion and increase the pressure slightly. The test monitors the boiler's response to increased internal pressure under controlled combustion conditions, ensuring the stability and safety of the system. To begin the startup procedure, the operator performs a quick visual inspection of the stable motor to ensure everything is in proper condition. First, they check the fuel tank and make sure the fuel valve is turned on to allow diesel to flow into the system. At the same time, the air intake is adjusted by partially closing the choke, enriching the air-fuel mixture for a smoother cold start. Before proceeding further, the engine is manually rocked to confirm that the piston and crankshaft rotate freely and that there are no internal obstructions. This careful preparation reduces the risk of starting difficulties and mechanical damage. Following this inspection, the operator initiates the manual cranking process. They grip the flywheel firmly and begin to rotate it with short, strong pulls. This repetitive motion helps draw fuel into the combustion chamber and bleeds air from the fuel lines. Each pull is executed with controlled strength and consistent rhythm, ensuring internal pressure builds gradually without overloading the mechanism. After several rotations, the engine begins to show signs of internal compression and light backfiring signals that the fuel-air mixture is nearing ignition. At this point, the operator adjusts the air and fuel mixture further. The choke is slowly opened to introduce more air and balance the mixture, improving combustibility. Additionally, they may engage a priming plunger to inject more diesel into the injector line, ensuring that the combustion chamber is adequately supplied. After making these adjustments, they continue to crank the flywheel to distribute the refined mixture evenly inside the engine. Eventually, the engine responds with more frequent combustion attempts. The operator increases the speed and intensity of the cranking. After a few more strong pulls, the engine sputters and catches for a few seconds before stalling. Recognizing that it is close to starting, the operator fully opens the choke and prepares for one final crank. With another sharp turn of the flywheel, the engine ignites successfully and begins to run on its own. The operator then gently adjusts the throttle lever to raise the RPM slightly, maintaining engine stability. Once the engine runs without external assistance, the flywheel is no longer touched. With the engine now self-running, the operator closely monitors its performance. They listen carefully to the rhythm of the combustion and check for unusual vibrations or irregular knocking sounds. The exhaust releases a steady, rhythmic pulse, confirming that the internal cycle is balanced. Additionally, the operator checks for any signs of leakage around fuel lines, injectors, or joints. Minor adjustments are made to the throttle to achieve optimal idle speed, typically between 500 and 800 RPM. Satisfied with the engine's behavior, the operator steps back. Finally, The warm-up phase begins. Rather than placing the engine under immediate load, it is allowed to run at low RPM for several minutes. This gradual warm-up period ensures that internal components are fully lubricated, thermal expansion stabilizes, and oil pressure builds to safe levels. The operator watches the engine carefully during this time, verifying that the temperature rises evenly and no issues emerge. Only after the engine reaches operating temperature is it ready for continuous or heavy-duty operation. Through this methodical and precise sequence inspection, cranking, adjustment, ignition, monitoring, and warm-up, the stable motor is brought from a cold start to a reliable, smooth running condition, ready for any workload. The Crossley Type K engine starts slowly, its massive flywheels gaining momentum as it fires intermittently in hit-and-miss fashion. It runs with a loud rhythmic pop, the governor adjusting fuel delivery to maintain speed. Nearby, the McDonald's Super Diesel fires up with thick smoke and strong, deep thumps, running at low RPM with reliable diesel power. The 1912 IHC Famous operates with exposed pushrods and rockers moving rapidly, firing at regular intervals as the operator fine-tunes its speed with a throttle lever. The Ronaldson Tippett CH diesel, connected to a Dunlite 32-volt lighting plant, starts with a few cranks and puffs of exhaust, quickly settling into a steady diesel beat. The generator spins smoothly, showing the early rural electrification method. The 7-horsepower Allen Bros engine, with its open crank and flywheel design, runs at a slow and steady pace, delivering rotary power via a flat belt. The 6-horsepower Lister CS diesel makes its signature slow, chuffing sound, the exposed fuel pump and injector mechanism working in time with the engine. The Lister A, paired with the Myers pump, draws water steadily, the water splashing as it flows through clear piping. Next to it, the 3-horsepower Moffett Virtue engine powers a Metters pump, the belt driving the pump's flywheel and pistons to move water. The 2-horsepower Sundex, connected to a drag saw, runs at moderate speed, its blade moving back and forth over a log in a sawing motion. The belt tension is adjusted by the operator to keep the saw consistent. The 4-horsepower Hornsby petrol engine operates with loud ignition pops and visible exhaust, while the 4-horsepower IHC Famous fires more quietly, but with the same open crank charm. The 6-horsepower K-Lister engine runs with a consistent beat, driving a pulley via a belt. Its fuel and cooling systems are managed manually. The 1.5-horsepower IHCM type, linked to a Boss pump, uses belt power to lift water into a trough. The 1-horsepower IHC Tom Thumb, compact and efficient, drives a small flywheel and linkage system, while a wooden working model of the same engine is seen running nearby, demonstrating precise scale functionality. The 2-horsepower Buzzacott, with bright red paint and simple controls, runs a vertical pump. The Fuller & Johnson farm pumper, with its broad flywheels, delivers pulsing motion to a water pump with a wooden piston rod. The Kelly & Lewis Triumph engine operates at medium speed with smooth action, the linkage driving a pump or fan. Another Lister A turns a belt to power an Ajax pump, which lifts water in steady spurts. A Southern Cross engine, fitted with a large pulley, runs a pump with a long connecting rod. The Ronaldson Tippett diesel thuds heavily with a deep exhaust note, running a small piece of equipment via belt drive. The 3-horsepower Sunshine engine, painted green and yellow, runs with a jerky yet reliable motion. Another petrol Hornsby engine turns over slowly but steadily, its flywheels smooth and silent between firing strokes. The Fowler plowing engine, an enormous steam traction engine, shows its gears, linkages, and massive flywheel turning as it simulates field movement. The Paisley engine, running at low RPM, operates a belt-driven attachment slowly and powerfully. A McDonnell diesel powers a Bagshaw winnower, which spins grain through vibrating screens to remove husks. The Sunshine hay baler compresses dry grass into rectangular bales. The engine spins the baler's chain drive and reciprocating parts, while operators feed hay and monitor bale ejection. A New Way engine runs quietly, possibly driving a small pump or tool. A large collection of chainsaws is also shown operating, cutting through logs with high-pitched whines. Finally, the axe handle-making machine is in motion, shaping wooden handles from square blanks. Its rotating cutters, feed rollers, and pattern guides work together in rhythmic synchronization, creating smooth, uniform handles from rough wood. Each engine is meticulously maintained and operated, offering a hands-on demonstration of early 20th century agricultural and industrial power. The hay baling process begins with the preparation of the ropes. Each rope is first twisted to form a loop, then stretched and cut to the correct length. These ropes are then used to tie the bales. The hay is fed by the operator into the hay baler chute. The stop ram, also known as the magpie, pushes the hay into the main chamber at consistent measurements. Once the hay reaches the chamber, the bottom ram compresses the hay with force, shaping the hay and folding the top layer over to form a neat bale. When the hay bale reaches the set length, a wooden divider board is manually inserted at the measured interface. This board separates each bale of hay and includes slots for the ropes to be threaded through. The pre-cut ropes are then threaded through these slots, 2 on each side of the board. The straight end of each rope is threaded through the twist on the other side. The rope is pulled taut to further compress the hay and then twisted several times by hand using a special tool, securing the hay bale tightly. This cycle repeats itself over and over again as the hay is pushed, compressed, divided, tied, and then ejected as a complete bale. The operator moves steadily along the press, manipulating the dividing plates and ties, ensuring that each bale is uniform, dense, and tightly tied, ready for stacking or shipping. The operator fills the boiler and ignites the fire to produce steam. As pressure builds, steam enters the cylinder, pushing the piston forward. The piston activates a rotary valve, allowing steam to flow in and out of two cylinders. This motion turns a crankshaft connected to the front wheel, propelling the vehicle. The operator adjusts controls to regulate speed and direction. The steam is gradually released, and the process repeats, enabling the fardier to move under its own power. The BD264 diesel engine starts on gasoline and warms up before switching to diesel. Once running, the tractor's live PTO drives the side-mounted electrical generator. The 10 kilowatts GE unit supplies power to an IH Model 55 hay baler, equipped with a 15 horsepower electric motor, replacing its usual gasoline engine. At Hill Farm, the Steam Plow Club's Great Challenge brought together 10 working steam plowing sets. Each set comprised 2 engines positioned on opposite headlands, using winding drums to pull a plow across the field via steel cables. As one engine wound in the rope, the other paid it out, pulling the implement smoothly across. After each pass, the roles were reversed, and the engines edged forward to begin a new furrow. On Plot A, Jonathan Garman's 1916 Fowler BB engine and Andrew L. Rose's 1870 Fowler single-cylinder Margaret, the oldest engine present, were used with a 4-furrow semi-digger plow. The team synchronized carefully to coordinate winding and releasing operations, producing even furrows. On Plot B, a matched pair of 1918 Fowler BB1S worked together. Ajax, owned by Peter Wilson, and Achilles, owned by Michael Davis. Originally built as a pair, they operated with precision, drawing the plow steadily across the field, aided by consistent rope handling and coordinated engine movement. Plot C was worked by Alan Sparks and his team. After arriving and positioning the engines, they connected the plow and began testing rope tension. Initial pulls were used to fine-tune alignment before full-speed plowing began. The steady rhythm of winding and unwinding the rope allowed the team to generate parallel furrows with minimal deviation. On Plot D, Daniels McLaren and Basil Gibbons had difficulty bringing their converted Mercedes diesel engine into place. Eventually, the engine reached the plot and was paired with a traditional steam engine to begin operations. At the top of the farm on Plot E, Mark Jones operated a Fowler K7, while Howard Bolton controlled a BB1. After 6 test pulls, they had their plow alignment dialed in. They began turning furrows confidently. Mark commented on their progress, noting the brown bit is at the top, a good sign of correct soil inversion. Plot F featured Mark and Jeremy Walker's diesel-converted 1917 Fowler BB Salty, matched with Mike's 16-horsepower 1918 BB1. Their 5-shear plow created tidy furrows. They moved carefully and deliberately, prioritizing quality over speed. The steepest ground, Plot K, was assigned to two 22-horsepower Fowler Z7 engines recovered from Mozambique. Although not a perfectly matched pair, both engines built in 1922 handled the 6-furrow plow well, hauling it uphill with ease and control. Lastly, a rare setup was seen on another part of Plot D, where Charles and Robin Daniels' 1916 horsepower McLaren Hero, the only non-Fowler engine, was paired with a BB1 Mercedes diesel conversion. Despite their differences, the two engines successfully managed the field, demonstrating adaptability across historic equipment. Throughout the weekend, each team plowed methodically, showcasing authentic steam plowing techniques with historical precision and pride. The operator starts the 1956 Caterpillar D25J dozer and slowly moves it forward. He adjusts the Cat 2A angling blade by changing its angle manually. Once set, the dozer pushes dirt effectively to the right side. As it moves, the wide 16-inch track shoes provide stable traction. The machine continues working across the field, demonstrating its ability to move soil with controlled, steady power. The D2's four-cylinder Cat D311 diesel engine provides the torque needed to push earth efficiently. The operator makes smooth turns, realigns the blade angle, and resumes pushing, showing the dozer's versatility in land grading tasks. Steam is supplied to the cylinder, driving the piston back and forth. This motion is converted to rotary motion by the crankshaft and flywheel. The large rear wheels rotate, propelling the engine forward. The operator adjusts speed and direction using levers, while steam pressure is monitored throughout operation.